folks, and welcome back to Physics with Captain Rod. I'm making this video to try to describe for you Newton's theory of gravity. Now, gravity is taught, kind of a couple different ways. And in a high school level or even lower level type of science book, gravity really is taught as an acceleration. Imagine this person in this picture holding this rock out. And if this person dropped the rock, it's quite easy to show by experiment that this rock will accelerate down at about 9.8 meter per second, or 9.8 meter per second squared, meaning that the velocity of that rock will increase at about 9.8 meters per second every second. And this numerical value here, this acceleration, is taught to be what gravity is. Or at least in some books it is. And gravity really isn't an acceleration, right? Gravity, in Newton's description, is a vector field. And the term vector, a vector is a quantity that has magnitude and direction. So in Newton's theory of gravity, gravity is described as a field of vectors. And when you make up a mathematical concept like this, you have to define it. So here's how gravity is defined in Newton's theory of gravity. So this person could quite easily measure the gravitational force acting on this mass, and that force direction would be down. Right? The gravitational field at that point in space is defined as force per unit mass. So if this person were to measure the gravitational force acting on this rock and then divide by the mass of the rock, this person will get a value of 9.8 Newton per kilogram. The 9.8 Newton per kilogram is the gravitational field strength pretty well anywhere at the surface of the Earth. And what that means is if I take a 1 kilogram object and I'm anywhere at the surface of the Earth, that object will feel a gravitational force of about 9.8 newtons. Now, the direction of the gravitational field is defined by the force direction. And since basically anywhere on the surface of the Earth you are, that force direction will be down, therefore the gravitational force or gravitational field vectors are down. So in Newton's theory of gravity, you can imagine a field of vectors in this room. I'm going to go ahead and draw a bunch of them. And that field of vectors, these would all have the same length, and they would be distributed uniformly. And that's because the gravitational field in this room is not changing significantly from point to point. If I take a gravitational field measurement here, here, or here, you're going to get basically the same value, about 9.8 Newton per kilogram, and it'll be pointed down. Now, in the confines of this room, the gravitational field would generally be considered to be constant, right? But that's not true in all cases. If we look at the Earth from far enough away, there's a completely different story taking place. So I'm going to go ahead and draw another picture to illustrate that. Right? So, if we look at the Earth from a long, long, long way away, in Newton's theory of gravity, the Earth creates around it what we would call a gravitational field. And the field vectors point inward. And that's because if I take a mass and I put that mass right here and I measure the gravitational force on it, well, the gravitational force is an attractive force. So that force direction will be this way, towards the center of the Earth. And if I take a force measurement on any mass, anywhere on this circle, the force direction will be basically towards the center of the Earth. Now, if I take that force, divide by mass, I'm going to get a numerical value that's going to give me the gravitational field strength anywhere, along this path here. Now, that number might be something like 4 Newton per kilogram, maybe 5 or something like that. I'd have to know the exact heights to calculate it. Well, the further out you go and you take the measurements, the gravitational field gets weaker and weaker. So the further out you go, you would represent that field with shorter and shorter vectors. So if I were to go around anywhere on this surface right here, right, that surface is roughly equal distance from the Earth anywhere, again, to within just a sketch. So the gravitational field vectors would be about the same length. So I could go on that surface, and I could represent the gravitational field with vectors. They would all be roughly the same, and they all point towards the surface of the Earth. or I'm sorry, the center of the Earth. If I go further out onto, let's say this distance, again, the gravitational field vector here, here, and here would all be roughly the same because they're all roughly the same distance from the center of the Earth. So I would have to draw all my field vectors about the same length as this one. And I would want to do that uniformly around, right, because the gravitational field is reasonably uniform around the Earth. And if I go further out, I can draw more field vectors, but they would be shorter because the gravitational field is weaker. Right? And imagine drawing just like thousands and thousands and thousands of these. So what I'm drawing, what I'm mapping out is the vector field. It's a field of vectors that describe the gravitational field around the Earth. So again, it's important to know how that field is defined. In Newton's theory of gravity, the gravitational field vector is defined as force per unit mass. So what this means is if you're to take an object and somehow measure the gravitational force acting on it, divide by the mass of that object, that would give you the gravitational field vector at that point. Right? Typically we use this relationship like this. We use it to calculate gravitational forces. The gravitational force acting on an object is equal to mass times the gravitational field at that point. In standard, college level physics, we usually just call this mg, and we use it when we're drawing free bodies to calculate the weight of an object. So I hope this helps describe a little bit about what gravity is. I'm going to go back and talk about, again, a free-falling object in the confines of a room. So I'm going to pause this for just a second. All right, I'm back, and I'm back to kind of my original picture here, and this is my buddy Bob here, imagine, and Bob is holding, again, a rock. And if I were to draw a free body of that rock right now, right, we got the rock sitting here, Bob is applying a force up, and that's an example of what we would call a normal force, or we could call it something else. I could call it F sub B for Bob or something. I'm going to go ahead and just call it N for normal force. Then the gravitational force points down, and that's equal to mg. And this force really is coming from the definition of the gravitational field strength. Right? Now, if I were to write a Newton's second law equation for that free body, it's kind of a boring one, but we would have N minus mg equals 0, and the normal would therefore equal the weight. Right? Now imagine that Bob drops the rock. So now what's going to happen is, in the free body, the normal force is going to go away. I'm going to try to erase this here. Right? So once Bob drops the rock in the free body, the only force is equal to mg, until the rock starts moving a little bit. Now, once the rock starts moving a reasonable speed, then there'd be a little bit of air drag, and I'll talk about that case here in a minute. So for right now, let's just look at the case where the rock, let's say, is reasonably heavy, and we approximate air drag as to being negligible in this problem. Then when we apply Newton's second law, sum of all forces equals mass times acceleration, calling down positive. My standard rule of thumb is to identify the acceleration direction, call that positive. Then what we get is that the force, mg, is equal to the right-hand side, which is ma. And because they're the same mass, we get that g is equal to a. Now what this means is that the acceleration is numerically the same as the gravitational field strength, right? And this is why a lot of textbooks tend to describe gravity as an acceleration, because if there are no other forces involved, they are in fact equal. But I wouldn't say that means they're the same thing. I mean, they have the same numerical value, but I think conceptually they are a little different. To me, the gravitational field is causing the force, and the force is what's causing the acceleration. So, when I kind of think chicken and the egg here, to me, g is coming first, causing the acceleration. I think that's a little more clear if we look at a free body of an object, like a soccer ball or something that's falling through the air. If I go back and I replace all this with a soccer ball, and Bob drops the soccer ball, well, now when the soccer ball is falling, if I drew a free body of that soccer ball, its gravitational force might be down. However, a soccer ball is has a lot of surface area compared to its mass, and what that means is air drag is typically a pretty important force for a soccer ball. So the air drag might be up. Or, I'm sorry, not might, but the air drag force would be up. Air drag always opposes the motion of a system. You know, when a system is moving through a fluid, the drag forces are in the opposite direction of the velocity. Now, you know, as long as the soccer ball is not going really fast, you know, kind of early on, right after Bob drops the ball, the gravitational force is still going to be larger than the air drag, and the ball will be accelerating. So if I apply Newton's second law to the ball now, sum of all forces equals ma, and again, identify the acceleration direction, call that positive. The net force acting on this ball is going to be mg minus that air drag force, right? And that equals ma. Now, when I solve for the acceleration of the ball, we're going to get g minus that air drag force over m. So the acceleration is no longer going to be equal to g. Now, one thing that I want to point out, you know, g is still the same as it was before. The g anywhere on this page here represents 9.8 Newton per kilogram. That's the gravitational field strength here at the surface of the Earth. If there are no other forces acting on a falling system, then the acceleration and g will numerically be the same. But in the example of, pardon me just a moment. All right, I'm back, folks. Sorry about that. I had to answer the phone. So let's see, where was I? Again, I'm looking at these two cases, case on the left, case on the right. Case on the left here, this is a free body of a rock, or imagine something fairly heavy. You know, for a heavy object, air drag, not a significant force. Therefore, the only force is equal to mg. And when you apply Newton's second law, the acceleration and the g are numerically the same. But I want to point out that's a consequence of Newton's second law. That doesn't mean that the acceleration is identically the same thing as the gravitational field vector, or the gravitational field strength at that point. And the example on the right, I think, clearly shows that they're not the same thing. All right, if we draw a free body of something like a soccer ball where air drag is a relevant force, then, you know, the Newton's second law equation would look something like this, mg minus f equals ma. And now when you solve for a, you know, the acceleration is going to be some numerical value less than g, because it's g minus, you know, some number. It doesn't matter what that number is. The important thing to realize is that the acceleration is now smaller than g, definitively. And I think that shows that these things just are not the same thing. G is the gravitational force vector, the gravitational field vector causing basically this gravitational force, or I should say is related to that gravitational force. A is the acceleration of the system with all forces taken into account. So anyway, I hope that this at least somewhat demonstrates or gets the point across about Newton's theory of gravity. Again, Newton describes gravity as a vector field. And the magnitude of that field is force per unit mass, and the most common way we use that is calculating gravitational forces in free bodies, mg. So, hope you have a great day. Talk to you soon.